Hello, this is Michael Shakib from Swansea University and Project Metal, and in this video we are going to explore some methods to try and determine the average grain size of a polycrystalline material using something called the mean linear intercept method. So if we take a piece of metal and study it, and examine it under a microscope, what we'll find is something like this. I'm going to make an expanded view here. I'm going to draw a schematic diagram of what you might see. So if we go through a process of polishing and etching this material, and we look at it under a microscope, what we'll find is that this piece of metal, and most pieces of metal, most metallic structures, are made up of individual grains. And we call this a microstructure, a grain structure. And each one of these grains is actually a single crystal. And many single crystals in one single structure is called a polycrystalline grain structure. So each one of these white areas here is an individual grain, and many of these grains together make up structures that we call polycrystalline structures or microstructures. Now the reason we call these microstructures is because these grains are normally in the sort of size range of micrometers and can usually only be seen under a microscope, so hence the term microstructures. And also it's something we need to note as well, that the only reason we can see these grains is because we have revealed the grain boundaries by using the methods of polishing and etching. And so this white area is the grain itself, the single crystal, and surrounding this grain is a grain boundary. It's very important that we understand that at this stage. Okay, so now we have this information, hopefully we can appreciate this information, and so the question remains, well, what's the point of all this? What is our motivation for actually studying this? So let's take an example of using a piece of carbon steel. In this case, we're using a 0.4 weight carbon steel. And you've got two images there on the top of the screen. And the first thing to note about these images is they are exactly the same magnification. Okay? But they look completely different. The image on the left-hand side has got a much, much smaller grain size than the image on the right-hand side. Now, why does that matter? Well, if we do a tensile test, which means basically pulling these materials apart, what we find is that actually the orange curve matches up with the smaller grain size and the blue curve matches up with the larger grain size. And what we find is that the yield stress and ultimate tensile stress is actually a lot larger for a given smaller grain size of a material. And with that, the ductility is dramatically decreased with a smaller grain size of material. And we call this behaviour the Hall-Petch relationship. And what is the Hall-Petch relationship? Well, let's have a look at this graph here. So this graph on the x-axis represents the grain size of the material. Don't worry too much about the units. And on the y-axis it represents the yield stress of the material. Okay? Now what you need to notice about the x-axis is it's the reciprocal of grain size. So it means basically the lower the number, the larger the grain size. And so down in this end of the graph, our grain size is around about 0.03 millimeters, whereas up here it's around about 0.07 millimeters. But what does this graph tell us anyway? Well, it tells us that the smaller the grain size, the higher the yield stress of a material, which we proved here already. Okay, we proved this already with actual tests from the laboratory. And so it can be seen that the grain size actually has a fairly profound effect on the mechanical properties of a material, which is useful to know. The grain size also has other effects, but I've just used this as an example. And so we need to be in a position where we can quantify the grain size of the particular material. Okay, it's no use just making comparisons like we've done here. We need to kind of find a way of quantifying the grain size so we can make a graph or something like this. I mean, it's especially prevalent if you work in sort of the forming of steel in industry where you're forming steel. You need to know the grain size of your material, and so you can work out the formability characteristics. And to do this quantifiable approach, we are going to use something called the mean linear intercept method. So if we take a look at the diagram we saw previously, which is the piece of metal and the grain structure that we revealed with etching and polishing and etching, and let's expand it up a little bit to give us a more clearer view. Now, someone might ask you, and you may ask yourself, how am I going to measure the grain size? What is the average grain size of this particular material, of this microstructure? There's a couple of ways we can go about doing this. One of them is we can measure every single grain, right? And then we can take an average. And when I say measure every single grain, we might sort of measure the grain in this direction, and then we go on to the next grain and kind of do as many measurements as possible to try and determine an average grain size of some kind. Some pieces of software out there that can help you do this. This is an extremely time-consuming way of doing things. And so a guy called Hayne in 1903 published this thing called the mean linear intercept method. But what is it? So if we drew a line across our microstructure here, okay, we can say a few things. If we know the length of this line, or even if we don't know the length of this line for now, what we can say is that we can count how many grains actually touch this line. Yeah. And for a given length of line, if more grains touch it or intersect it or intercept it, we can say that actually the grain size is smaller. And if less grains intercept or intersect this line, then we can say that the grain size is larger. And that's a really simple, powerful method of determining the average grain size of a material. And that's all a mean linear intercept method really is. Now, it doesn't have to be a line that goes horizontally. It can be at an angle. It can be vertically. It doesn't really matter. There are even circular intercept methods where you draw a circle and you take the circumference of the circle. So that's the essence of the method. Now we'll go in and look at it a little bit more deeply using this equation here. And so if we use this equation here, which is the mean linear intercept, so the mean linear intercept is equal to the average grain size of the material, and it's equal to the length of your line that you've drawn on your microstructure divided by the number of grains that have been intercepted. However, there's a bit of a twist to this story because it can also be measured as L over P. Now what is P? P and N are different, okay? P is the number of grain boundaries intersected, and N is the number of grain boundaries intercepted. Now this is made really clear in this particular standard here. And I'll tell you what, if you're going to get serious about measuring grain sizes, okay, using this method and any other method you choose to use, you really need to have a look at the ASTM E112 standard test method for determining average grain size, or the one we're going to use in this presentation, which is the British standard EN ISO 643-2012 steel micrographic determination of apparent grain size. This is the one we're going to be using. And it makes a clear distinction between the number of grain boundaries intercepted and the number of grain boundaries intersected. So I'm going to do an example. So first of all, let's look at N. Find the number of find the number of intercepts. So what do? Well, first of all, we take a random line, or we draw a random line of known length onto your microstructure. We then count the number of intercepts, N, and there's a few rules we have to obey here. If the test line goes through a grain, then we say that N equals 1. If the test line terminates within a grain, then we say that N equals 0.5, and if the test line is tangential to a grain boundary, then we say that N is equal to 0.5 again. So what I've got here is two fictitious grain structures, grain structure A and grain structure B, and we're going to count N. So the first thing I've done is drawn this red line across the microstructure. Now that's all I've got to do is count the number of grains that are intercepted, let me get the wording right, intercepted by this line. So here's our first grain, and we call this 0.5. I call this 0.5 because it's terminated within a grain. I can't see the edge of this grain, this boundary. I don't know for sure if this red line is going to intercept this particular boundary here. So I've called it 0.5. As we go along this line, we can start counting. Well, the line intercepts this grain here, call that 1, this one, another grain. Now, this is a tangent, okay? This is a tangential grain boundary, so we call that 0.5. But what does a tangential grain boundary mean? Well, if we take this circular arc to be a grain, and this to be a test line, the black line to be a test line, this particular test line is now at a tangent to this grain boundary. It doesn't go through it, it just goes on a tangent to it, just touches the edge of it. So we call that 0.5 for this particular grain here. Now the test line terminates within this grain, so we call that 0.5. It's counted as 0.5. Now if we simply just add these up, we come to a situation where we have the average grain size equals L, the length of the line, divided by N, the number of intercepts, and so we have L over 5.5. Now we can clearly see grain structure B just by looking at it. It's not difficult to see that actually these grains are smaller than these grains. Grain structure B is smaller than grain structure A. Yeah, you can just tell that by looking at it. There's more grains there and they're definitely smaller. Let's say for now that these structures are at exactly the same magnification. It's very important that we establish that in the very beginning. So again, we'll go through a series of counting how many intercepts there are to this red line. So we've got 1 there, 1 there, 1 there, another tangent 0.5, 1, 1, 1, 1, another tangent 0.5, a full grain, and a grain that terminates somewhere where we just can't see. So we'll call that 0.5. And so if we add all these numbers up, that comes to 10.5. Again, we can say that the average grain size is the length of the line divided by N. So in this case, it's L over 10.5. So obviously now, given that the two test lines are exactly the same length, we're in a situation where we can see the amount of intercepts is the denominator. As this gets larger, the grain size also gets smaller. Okay. So how does this change if we look at the number of intersects, which we call in P in this case, this is what the standard says. The same process is done. You draw a random line of known length, but in this case, you count the number of grain boundaries intersected, okay? And there's a slight difference, and it will be very clear when I show you. So if the test line goes through a grain, we count this as 1, as before. If the test line is tangential to a grain boundary, then we count this as 1. But if the test line intersects a triple point, then we call this 1.5. How does this work? Well, again, we've got exactly the same grain structure A and B. But now we're going to count P, okay? P is the number of intersects. So there's no grain boundary intersected in this grain here. Our first grain boundary intersect is here, 1. Our second one is here, our third one is here, our fourth one is here. Now we hit a triple point where 3 grain boundaries hit each other at this point here, and we call this 1.5. Again, we cannot count this grain. We're not using the other method, we're using counting the number of grain boundaries intersected, and so we'll leave this to be 0. And if we count these up, you find that P equals 5.5, the same as N equals 5.5, P equals 5.5. It's exactly the same. So we've got the same answer in this situation, whether we use N or P. And that's what should happen. Actually, in theory, that is what the standard says should happen. It doesn't matter which one of these methods you use. Use P or N, it doesn't matter. You just have to keep things consistent. Now, something different happens when we look at grain structure B, and I'll try and explain as best I can. Let's start our regular counting method. So this grain here is sort of off screen, so I kind of could make an assumption that grain boundary would intercept this line, but I'm not going to for now, okay? So our first grain boundary intersection here is 1. We have a triple point here, 1.5, another one, another one, another one, another one, another triple point here, and another grain boundary here, another grain boundary there. So it's terminating within this grain. So we don't count this grain, we just count this boundary. Now if we used N, the number of intercepts, we found previously that the number of grain boundaries intercepted was 10.5. Now when we use the method and we calculate for P, which is number of grain boundary intersects, what we find is the answer comes to 10. And so there's a 0.5 discrepancy here between the number of, well, N and P basically. That's a bit of an issue. I think I've kind of narrowed it down to this point here, which causes us a bit of confusion. Let's have a look at this particular point here in more detail. Now, if we do zoom the micrograph in, okay, what we'll see here is actually that this line may not quite be a triple point. Well, in the case of N, we may not be at a tangent. So, we could potentially count this grain here as 1 instead of 0.5. And so what that does is it makes N equal to 11 instead of 10.5. Okay, so how is that really affecting us in terms of what P is counted as? Well, if we look in terms of P, well, we could say that if this is not a triple point, then this is an intersect and this is an intersect, then what we should do is count this particular portion here as 2 instead of 1.5. And that drags us up to P of 10.5. Still, they're not equal. And actually, I've read a few reports online about saying when you come to this sort of situation, there can be a slight discrepancy between N and P, but the more you do, okay, the greater the accuracy of results. So just stick with one method and just go with it. That's kind of the message I think we should go with for the rest of this presentation. Now, if you are going to get serious about using these test methods for your micrographs, your microstructures, you have to kind of understand that you need to operate under some constraints, okay? And there are some assumptions which are explained in the test standards, which you're going to have to operate under. And so the first assumption, which is fairly explicit in both test standards, is that the grains that you're looking at need to be equiaxed. Okay, that means they need to be generally similar dimensions in every direction. Now that may not be possible, and what you'll find is that you're never going to get a microstructure that's entirely equiaxed, but they need to be generally similar in every direction. And we'll have a look at an example later that explains that a bit more. The grain boundaries have to be clear, obviously, because you need to count them. And the first sections of both these standards are dedicated to looking at methods for actually doing this. One of the important things is you need to understand that to do this properly, you need to be looking at single phase structures. And I'll cover that in a video after this video. There needs to be at least 50 grains in view. And really you need to take at least 5 randomly selected fields and have a total of 250 grains. I mean, the more intercepts that you do, the more accurate your results become. Okay, so the more you do, the more accurate the results become. It's as simple as that. It just takes more time, obviously. And you need to have a clear magnification bar, or just a clear understanding of your magnification of your image. And so let's try and apply what we've learnt already to a real-life example. Now this is a microstructure. This is a micrograph. When I say micrograph, it's just another way of saying sort of an image taken on a microscope. It's a microstructure, a micrograph of some commercially pure titanium. And I want to measure the average grain size in this piece of titanium. Okay. Well, first of all, we need to look at the assumptions that we talked about earlier. And the first assumption is having equiaxed grains. And I can see that from this microstructure, just by looking at it, I've taken a grain down here as just one example. What you'll find is, yeah, these grains are generally similar size in every direction. Okay, so I'm happy with that. I'm happy with our first assumption. And there's another example up here which shows that. This grain's slightly different. Remember I was talking about you're never going to get perfection. Well, it's true. So this grain is slightly longer in this direction than this direction. So it's not perfect, but it's good enough. I'm happy that we have equiaxed grains generally similar in every direction. But what else? Well, the grain boundaries are very clear. This is actually taken under a polarized light microscope, which gives excellent contrast between the grains. So we do have very clear grain boundaries in this case. This is a single phase structure and I'm going to cover that again in a separate video. We definitely have at least 50 grains in this image, and we definitely have a clear magnification bar that I can trust. And the magnification bar here shows 500 microns from the end of this black line to the other end of this black line. And so what's the next step from here? Well, it's quite simple. That's all I've done is I've taken this image and I've drawn a line, this blue line here, right across the image. I haven't worked out the length of it yet. Don't worry about that for now. I just want to talk about the counting technique. So in this case, we're looking at n, the number of grains intercepted. And so that's all I do is I start counting. There's a half a grain there because the line terminates within the grain. 1, 1, 1. And I just recommend you sort of pause this video and go through it and try and figure out what I've done. I may have made a few mistakes. If I have, just point them out. And if I add all these up, what we'll find is that n is equal to 18. Now I can do exactly the same thing for p, which is just looking at the grain boundaries intersected. And so we'll start here and we'll do the same thing. We'll go along and we've got a couple of triple points here, which are equal to 1.5. And what you find is that p and n have come out to exactly the same number, 18, which is fantastic. That should be the case. Most of the time it should be the case. And so really it's up to you which technique that you want to use, which one suits you. I actually prefer using p, the number of grain boundaries intersected. The test standard says there are certain circumstances where you may want to use p or n, depending on the type of method or microstructure you're looking at. But I usually use p, but use whichever one you want. It's up to you. Alright, so we found how many grains intercept, or how many grain boundaries intersect this particular line, but there's something missing. We have no idea at the moment how long this test line is, and so we need to figure that out. And to do this, I'm going to go through some sequential steps of trying to use these magnification bars and trying to understand magnification of images to try and figure out how long this test line is. And when we get an appreciation of how to do this, we can start applying it to easier methods of doing it, should we say. So the first thing I want you to sort of ask yourself, are the grains in image A bigger than image B? Okay, are the actual grains bigger in image A or image B? Well, what you'll find is that that's all I've done is I've taken image A and I've shrunk it down a little bit, okay, and I've called it image B. The grains are exactly the same size. Okay, the image is smaller, but the grains are exactly the same size. And so with that concept in mind, I think we can start trying to figure out just how long this test line is. Alright, so going back and taking a look at our image that we've been working with previously, I've emphasized the point quite a few times now that we need this magnification bar. This magnification bar is your on-screen ruler. You can think about it as the sort of scale of a map. And you have to have this, so you have to calibrate your image. You have to somehow get this magnification bar onto your image. Now it can sometimes it's done automatically via your microscope software system, which is usually the case these days. In the past, you had to take an image of a ruler or a graticule and superimpose it at the same magnification that you take your image at onto the image itself before you can, and then sort of try and make a nice looking mag bar like the one you see here. But the point is, this is what you use to measure any distance on your image. Yeah, so this magnification bar says it's 500 microns, and that's from the end of the black line one side to the end of the black line on the other side. So when it comes to figuring out magnification bars and just dealing with magnifications in general, I'll admit it can become quite confusing. And so I'm going to try and break it down in using a simple example, a rudimentary example, and see if it makes sense. If it doesn't, then we can always sort of redo this bit. Let me know in the comments. Alright, so if we take this image, okay, I've just taken this image off the internet. It's a boy and a tree. The boy looks like he's about to hug the tree. So if I ask you the question, how tall is this tree? Well, your answer should be something like, how should I know? And it's a valid answer to have. I mean, we have absolutely no idea how tall this tree is. We don't know what type of tree it is. We have no information whatsoever on how tall this tree is. I'll say, okay, fair enough. And so what if I give you some kind of reference? If I give you some kind of clue, and the clue is that this boy that's about to hug this tree, or worship this tree, is about 5 feet tall. That's approximately 1.5 meters. Alright, so the first thing I'll do is draw an arrow. I'll draw an arrow signifying the height of this boy. Sort of from his feet to the top of his head. That's how tall this boy is. And I'll write on it, I'll say that this boy is 5 feet tall. And if I spin this bar here, spin this arrow, and move it across, and I'll superimpose the image from before with a mag bar in it. Aha, now what we can see is that actually this magnification bar is exactly the same as this magnification bar here. We'll call this a mag bar now. We've taken a reference point in an image and we've said this boy is 5 feet tall. We've drawn an arrow and we moved it across. Now we have a magnification bar. And what we can do is just stack these up. If we stack these up, we can make a calculation. An approximate calculation, we can say, well, actually, this tree is approximately 3 times as tall as this boy. Now, if you want to be more specific, you may say, okay, well, the height of this tree is now 3 times 1.5 meters, which is about 4.5 meters. So we've used a reference in the image. And so in this image, the reference was the height of the boy. And in this image, we're using the reference as the mag bar. Okay, so hopefully that example has sort of sunk in and explained the importance of using magnification bars. And the good thing is, believe it or not now, we have enough information here to be able to figure out how large or small or the size of anything on this diagram. Okay, we can work out the length or the height of this grass here. We could work out the length of this boy's leg. It's just a matter of dividing or multiplying the amount of mag bars that fit into this particular thing. If the tree had leaves, we could figure out how big or small the size of each leaf was. So it's a very powerful technique that we've now got that we can use. Now let's have a look at our scientific commercially pure titanium diagram again, not diagram, microstructure again, and we have our magnification bar. So what can we do? Well, we can do exactly the same thing as I did in the previous diagram, just to show you as an example. If I take one of these magnification bars and I move it to the image, we now know that the distance from here to here is 500 micrometers. I can do that again. Yeah, I can double up. I can triple up. I can keep on increasing the length of this line. And so now we know that the length of this red line here is approximately 1500 micrometers. Okay? So now we know the length of our test line. That is a method, that is a rudimentary method of trying to figure out the length of a test line. And we can go through our counting method once more and then try and figure out what is the mean linear intercept or the average grain size of this particular micrograph. So there we go. Let's use this equation here. The mean linear intercept, or the average grain size, D, is equal to the length of the test line, which we now know through using our magnification bar and our knowledge, divided by P or N, and in this case I've used P, the number of grain boundary intersects. And we can say that the length of this test line is 1500 micrometers. P in this case is 25.5. And so D is simply equal to the length of the test line over P, which is 1500 over 25.5, which gives us an average grain size of 58.8 micrometers. Now remember, this is an average grain size. There are some grains which are bigger, there are some grains which are smaller. You can do statistical reviews on this, and you can do all sorts of other reviews on this and use all kinds of fancy programs to give you this. But this really is just the essence of using the mean linear intercept to get the average grain size. Now, I would not do it this way. I would use a very, very easy piece of software called ImageJ, or you can use Photoshop. You can use any bit of software to try and figure out the length of this test line. That's the thing, that's the key to this. You need to figure out the length of the test line, and the counting method then becomes very, very simple. Alright, so what's next? So in a couple of separate videos, I'm going to use a piece of software called ImageJ to do exactly what we've done here, but it will make your life a lot easier. Yeah, software tends to do that. I'm going to make another video talking about the limitations of this method, speaking more about what I meant by single phase alloys or single phase microstructures, and touch on how we may sort of do this for non-equiax structures. I'm also going to do a printed out version. Okay, so sometimes you'll just have a printed out microstructure and you need to figure out the grain size that way. And there's a good way of doing that. So I'm going to go through that as well. Alright, so thanks for listening. And hopefully you've got something from this video.